Hey everyone, and welcome to this explainer. So, if you're a college student trying to wrap your head around the fundamental forces actually powering your everyday life, well, you are definitely in the right place. Today we're taking a nice, calm look at those silent little chemical powerhouses that we rely on pretty much every single day. Yep, we are talking about batteries. Now get this, did you know the world produces over 15 billion batteries every single year? That's just wild. Whether it's the laptop you're using to crank out term papers, the phone that drags you out of bed for that 8 a.m. lecture, or even the emergency lights down your dorm hallway, we are literally surrounded by stored energy. But how exactly do they work? And why on earth are there so many different types? Let's unpack the invisible chemistry that's quietly powering your day.
Right, so to kick things off, I want you to just think about this for a second. Why does a smoke alarm battery sit quietly up there on your ceiling, lasting for literal years, while your smartphone is practically begging for a charger by dinner time? It's a super relatable frustration, right? We've all been there. But it actually points to something genuinely beautiful about chemical engineering. Because, as it turns out, not all portable power is created equal. Every single battery is meticulously designed for a very specific job, carefully balancing things like energy density, power output, and overall lifespan.
Okay, so before we start categorizing them, let's get our basics down. What exactly is a battery? At its absolute core, a battery is essentially a portable source of electrical energy. It works by combining one or more electrochemical cells to convert chemical energy straight into electrical energy. Think of it like a miniature, totally self-contained power plant. Inside that little casing, a chemical reaction is taking place that actually pushes electrons out through an external circuit. And that flow of electrons, that's the electricity powering your stuff. It's elegant, it's compact, and honestly, it is entirely chemistry at work.
Okay, moving into section 1, primary batteries, one and done.
So I kind of like to think of primary batteries as the incredibly dedicated volunteers of the battery world. They step up, they give you absolutely everything they've got, and when their energy is spent, they just step away. Take the classic dry cell, which is also known as a Leclanche cell. In these primary cells, the chemical reaction is strictly a one-way street. It is simply not reversible. So, as the battery powers your device, the active materials inside, stuff like zinc and manganese dioxide, are physically being chemically altered. And once all those reactants are fully converted, the battery is officially dead. You can't just shove electricity back into it to reverse the process. Once it's done, it's done.
Now, because you can't recharge them, primary batteries are absolutely perfect for what we call low-drain devices. You know, the things in your life that just sip power super slowly over months or years. Think about the alkaline batteries in your TV remote, or maybe the wall clock in the study lounge. Then you've got primary lithium cells, which are incredibly light but give a slightly higher voltage. Those are perfect for your scientific calculators or small cameras. And then silver oxide batteries are those tiny little button cells keeping your wristwatch ticking. They don't need a huge surge of power, just a nice, steady, reliable drip of energy.
All right, let's jump to section 2, secondary batteries, the rechargers.
Now, if primary batteries are the single-use heroes, secondary batteries are definitely your daily drivers. They're engineered from the ground up to perform this fascinating reversible chemical dance, which lets you use them over and over again. And what's really cool is that a secondary battery kind of has a dual personality. It acts as two totally different types of chemical cells depending on what you're doing. When you're actively using your device, like scrolling through social media, the battery is discharging. It's acting as what we call a galvanic cell, spontaneously converting its stored chemicals into electricity. But when you plug it into the wall, it transforms. It becomes an electrolytic cell. It uses the electricity from the outlet to physically force that internal chemical reaction to run backwards, packing that energy away as stored chemicals for tomorrow. To really picture this, let's peek inside a standard lithium-ion battery, probably almost identical to the one powering the device you're watching this explainer on right now. It's built with a positive electrode made of layers of a lithium metal oxide and a negative electrode made of layers of porous carbon, essentially graphite. When you charge and discharge the battery, actual physical lithium ions are migrating back and forth between those carbon and metal oxide layers, just swimming right through a polymer gel electrolyte. It's this quiet, continuous movement of ions happening right there in the palm of your hand.
So, the big takeaway here is that secondary batteries are designed for high-use, super demanding applications. Throwing away a battery every single day for these devices would just be insanely wasteful, right? We have the big, heavy-duty lead-acid batteries that crank your car engine in the morning.
We've got nickel-cadmium, or NiCad batteries, which are legendary for being sturdy enough for heavy power tools. And obviously, those incredibly energy-dense lithium-ion batteries, keeping your smartphones and laptops alive from your morning commute all the way through that late-night study session when you, totally forgot your charger.
And that brings us to Section 3, Reserve Batteries, Sleeping Giants.
So, unlike the batteries in our phones or remotes that are pretty much always ready to go, reserve batteries just patiently wait in the shadows. They are custom-built for extreme situations where failure is simply not an option, but the battery itself might literally need to sit in a box unused for decades. See, one of the biggest enemies of any battery is this annoying thing called self-discharge. Even if you're not using a normal battery, the chemicals inside are slowly reacting, and eventually, the battery just dies on the shelf. Reserve batteries solve this with a seriously brilliant trick. A key component, usually the active electrolyte, is kept entirely physically separated from the rest of the cell. Because the chemicals literally cannot touch each other, there is absolutely zero self-discharge. The battery just sits there perfectly dormant, kind of frozen in time, until the exact second it is needed.
And let me tell you, the way these things finally wake up is dramatic. Take the thermal battery, for example, which they use in aerospace and military missile guidance systems. The electrolyte inside is actually a solid block of salt. It does absolutely nothing until intense sudden heat is applied, melting that salt into a liquid and instantly activating the battery to deliver a massive surge of power. Or think about the water-activated battery. These are built directly into life jackets and emergency buoys. They sit there completely dead until they are submerged in the ocean. The moment they hit the water itself acts as the missing component, snapping the battery awake to power a life-saving light or an emergency radio beacon. Amazing, right?
Finally, let's wrap it all up with Section 4, the big picture, choosing the right power source.
Well, we've definitely covered a lot of ground today, all the way from the little batteries in your TV remote to the ones actively saving lives out at sea. And understanding these classifications really helps us appreciate how engineers figure out the absolute perfect power source for every single application. If you break it down, notice the stark contrast. Primary cells, they're non-reversible, single-use, absolutely great for low-power stuff like radios and torches. Secondary cells, highly reversible, meant to be recharged again and again, totally designed to do the heavy lifting for our electronics and electric vehicles. It's all about perfectly matching the chemistry to the human need.
You know, as you go about your classes and your daily routines, I genuinely hope this gives you a bit of a new perspective. Every electronic device you touch, from that watch on your wrist to the laptop sitting on your desk, has this silent, chemical heartbeat. It's not magic. It is meticulously chosen, incredibly thoughtful chemistry, all designed to make your life just a little bit easier, more connected, and a whole lot safer.
So, I'm going to leave you with this one thought. The next time you grab your charger and plug your phone into the wall or pop a fresh battery into that annoying beeping smoke alarm, just take a single second to appreciate it. Think about those billions of tiny lithium ions migrating back and forth, or that zinc chemically reacting. It's a totally invisible chemical dance that makes our modern lives possible. Kind of makes you wonder, doesn't it? What other unseen scientific marvels are just quietly powering your day? Thank you so much for joining me for this explainer. Keep asking questions, and I'll catch you guys next time.